Greetings, welcome to lecture number 8 on basic circuit theory. I am Razavi. Today we will switch gears to a different type of circuit analysis called mesh analysis. And we want to go through the steps that it takes to perform this type of analysis on a circuit. Mesh analysis is a different type compared to what we have seen, compared to node analysis. It's just a different approach, and one can choose node analysis or mesh analysis. I should mention that node analysis is quite intuitive and physical, whereas mesh analysis is not. Mesh analysis is more of a mathematical construct. So typically in circuit design, we do not use mesh analysis. We always use node analysis. But if your instructor insists on learning mesh analysis, here it is. We're going to go through it today. And then we will talk about the concept of excitation and response, and that will bring us to one circuit theorem that is extremely useful and is called superposition, which is based on linearity. So we'll go over these to create new ways of looking at circuits and understanding circuits. Now, before we go there, let's take a look at what we covered last time in lecture number 7. We talked about supernode analysis, and we saw that if a circuit contains a voltage source, then the standard steps that we had in node analysis fail, so we had to resort to two more steps. So one step was take this voltage source and the two nodes attached to it and call this whole thing, this green box, a supernode, so that we can write a KCL for the supernode, for all the wires that are going into this green box. Now, because we have voltage source, we lost a KCL, and that means that we have to be looking for a KVL. And the KVL that we're going to write consists of this voltage source and the voltages at these two nodes. So if I have a voltage here VA, another voltage here VB, and this voltage source, I can write a KVL for those three. And finally, we also noticed that if there's a voltage source connected between a node and ground, we do not try to create a supernode here, because that does not give us any additional information. The only thing that we can do is write a KVL, meaning that, say, this voltage with respect to ground is in fact equal to V1, and that's all we need. So today we will look at mesh analysis. We will see some similarities and some differences with respect to node analysis and also the concept of supernode. Now, before we go there, I wanted to look at this little lemma here. This is very useful, and we just have to make sure that we are not confused about the signs. Suppose I have a resistor R, and suppose I push two currents through it. One current from left to right, one current from right to left. So I1 going this way, I2 going this way. Where do they come from? It doesn't matter. They come from somewhere, right? So we just push two currents through it. Now, what we know is that I1 going from here to here wants to generate a voltage equal to I1 times R. And that voltage would have a positive on this side and negative on this side. So that voltage would be V is equal to I1 times R. But at the same time, another current is passing this way, called I2. That creates a voltage with a negative polarity, so we have to subtract that. So the total voltage that I measure with the high potential on this side and low potential on this side will be I1 minus I2 times R. It's important that you really get the hang of this with all the signs, etc., for mesh analysis. Okay, so let's talk about mesh analysis and see what it takes to perform this type of study of circuits. All right, so mesh analysis. So first I have to tell you what a mesh is. A mesh is a loop in a circuit. A loop meaning we start from a point and we come back to that point. But a mesh is a particular type of loop. It's a loop that does not contain any other loops within it. So it's the smallest loop you can find. So a mesh is a loop that does not contain any other loops within it. Okay, so as an example, suppose I have something like this, a voltage source, some resistors, etc. Okay, so I can identify a mesh. Here's one mesh, right? I go around this loop, that's a mesh. This is the smallest loop you can find. There's nothing else inside it. There's another mesh. Sure, this is another mesh, right? You go around this loop, that's another mesh. But this loop, this is a loop, right? This is a loop. This is a perfectly legitimate loop. That loop is not a mesh because it includes these two meshes. So this circuit has only two meshes. That's what we have to remember. It's pretty easy to identify the meshes because they're the smallest loop that you can have in each part of the circuit. Okay, so now mesh analysis proceeds in the following steps. So we have 3 steps. Number 1, we identify all of the meshes of the circuit. So identify all of the meshes and assign a current to each. Okay. All right. So this is somewhat unintuitive. As I said, this is more of a mathematical operation, but we have to do it for mesh analysis. So here's how it goes. I have a mesh here. I will say a current equal to, for example, I1 is flowing through this mesh. So I'm going to call this current I1. So I1 here. And then I say another current equal to, for example, I2 is flowing through this mesh. And I call that I2. All right? Which way do I pick the direction? It doesn't matter. It's up to you. So you can pick the direction clockwise or counterclockwise. It doesn't matter. Okay. So it's strange, right, that I'm assigning a current to each mesh or each loop. What does it really mean? So if I look at this resistor sees a current coming in here this way. It also sees a current coming this way, right? It's strange. Like here, right? We have a resistor with 2 currents through it. After all, if you go inside the resistor, there's always just a 1 current passing through it, right? It can be this way or it can be this way. But because we're dealing with this mathematically, we assume that there are actually 2 currents flowing through this resistor. So we have a current associated with this mesh, another one associated with this mesh. All right. So in the next step, what we will do is we write all the voltage drops that we can find. So write the voltage drops on the circuit. For example, if the resistor is called R1 and the current of I1 is flowing from left to right, then it generates a voltage across it, and that voltage would be positive here, negative here, and the voltage value will be I1 times R1. Okay. Similarly, this resistor has a current going from top to bottom called I2. So if this resistor is called R3, for example, then the voltage drop from here to here is I2 R3. All right. And then this resistor requires particular attention because we have a current going from top to bottom, I1. We have a current going from bottom to top, I2. So those 2 currents have to be added and multiplied by this resistor to give us a voltage drop, like what we saw here. So we'll deal with this a little more later. For now, don't worry about it. But of course, all of these have to come into play. Okay, so you can see some similarity between mesh analysis and node analysis, right? In node analysis, we assign voltages to nodes, and then try to find the currents through the branches and mark them on the circuit. Here we assign currents to meshes, and now we try to find voltages and mark them on the circuit, these voltage drops. All right, so that's the duality between node analysis and mesh analysis. Okay, in the next step, we will go forward and write a KVL around every mesh. So write a KVL around every mesh. So if the circuit has, for example, n meshes, we also write n KVLs. We have n meshes, therefore we have n currents. We write n KVLs, that gives us n equations to solve, and from those equations we can find all these currents, and once we have the currents we can find everything else. So what you can see is that unlike node analysis, we do not need to assign a ground here because we're not looking to assign voltages. Voltages always have to be with respect to somewhere. Here we just have currents that are looping around in these meshes. Okay, so these are the three basic steps necessary for mesh analysis. And let's go through an example just to get comfortable with the idea and see how the mechanics proceed. So, all right, let's look at this example here. So I have a voltage source, I have a resistor, so let's call this Vx. Then we have R1, then we have R2, let's see, and then we have another resistor here, R3, then we have a voltage source here, Vy, we call this resistor Vy, okay, let's see if this pen cooperates, all right, Vy, and these are all connected to each other, and we would like to solve the circuit. So Vx and Vy are known, and want to find all the currents and voltages and so on. Okay, we could perform node analysis if you want to. We have these voltage sources and we have to deal with them properly, but we could. Or we can just go with mesh analysis. So let's go with mesh analysis. All right, so step number one, identify all of the meshes. How many meshes do we have? We have two, right? One little loop here, one little loop here, right? This big loop doesn't count as a mesh because it already includes these two smaller loops. Okay, so we go with, we mark these. So let's mark this like this very carefully. We say this is a current of I1 flowing clockwise, starting from here, going through this, coming back. All right, and then we assign another current to this mesh. Again, we can make it clockwise or counterclockwise, doesn't matter. So I2. And now that we have two currents, we are done with step number one of the analysis, and we can go to step number two. We want to mark the voltage drops on the devices inside the circuit, inside the schematic, so that later on we can write KVLs. So how do we do that? Okay, we start from here. This is a voltage source, so that's given, no worries there. We have a resistor, and this resistor carries the current of I1 from left to right. So it generates a voltage across it, and that voltage is just given by the current times the resistance. So let's change the color so that stands out. So there's a voltage from here to here, and the value is given by I1 times R1. So that's I1 times R1. Okay, it's imperative that we place these positives and negatives properly, because later on we're going to write a KVL, and if these are not on the circuit, the KVL will be very confusing. All right, let's go to R3. What's the current through R3? I2. I2 happens to be going from left to right. So again, we have a voltage like so. How do I know it's positive here, negative here? Well, the current has to go from high potential to low potential, right? Same here. The current is going from high potential to low potential. So then this potential difference is given by I2 times R3. Okay, got those two. The only component that remains is R2, and R2 requires special attention. So let me draw R2 separately and see what's going on. So here's the situation with R2. So that's R2. And R2 in the scenario carries two currents. I1 is flowing from top to bottom. So I1 is going this way. And I2 is going from bottom to top. So I2 is going this way. And we would like to find the voltage drop across R2. First, we have to decide where we want to place the positive end of the voltage and where the negative end of the voltage. It's arbitrary. So for example, I will say my voltage will be like this, plus and minus. This is my voltage. And I want to find this value, the voltage that I have across R2. Well, if the voltage is high here, low here, then the current going from high to low is directly multiplied by the resistor to give me that voltage. So the current going from high to low, I1, gets multiplied by R2. Okay? And then there's a current that's going from low to high, this one. So that generates a negative voltage. So that has to be minus I2 R2. This is the voltage drop across this resistor with this sign, positive, negative. So we're going to write that here. I don't have room in the schematic, but I'll just put a little note here that this voltage drop is equal to I1 minus I2 times R2. And again, if you rotate this by 90 degrees, you can see the similarity between the two. Okay, so we completed step number 2. Now we go to step number 3 and write a KVL around every mesh. We have 2 meshes, we write 2 KVLs, we end up with 2 equations and 2 unknowns. The 2 unknowns are I1 and I2. Okay, so let's write our KVLs. I'm going to write a KVL around this loop. So starting from here, I'm going up the potential, so my plus Vx, going down the potential minus I1 R1, and then going down the potential positive to negative, and going down the potential takes a negative, and then I have to write this voltage, whatever it is. So that would be I1 minus I2 times R2 equals 0. Okay. All right. One more KVL around this mesh, starting anywhere we want. So let's say I start from here, going up the potential. So I'm going to write this voltage with a positive sign. So how much is that voltage? It's I1 minus I2 times R2. So I1 minus I2 times R2. Then I'm going to reach here and I go down this potential, high to low. So that's minus I2 R3. And then I go here and I'm going down the potential, minus Vy equals 0. So 2 equations, 2 unknowns, we can find I1 and I2. Once we have those, we can find anything else we want, right? This voltage is known, this voltage is known. This voltage is now I1 minus I2 times R2. We can find that, etc. Okay? All right, so a few interesting observations then. So let's change the color here. So 2 observations. So number 1, node analysis is KCL centric, meaning that it relies on KCLs, right? So node analysis is KCL centric. We keep writing KCLs to the extent that we can. And we also saw that has difficulty with voltage sources. So has difficulty with voltage sources. Right? So once you had a voltage source, we had to define a supernode and all that. Now, mesh analysis, on the other hand, so mesh analysis, as you can see, is a KVL-centric approach because we keep writing KVLs. So it's KVL-centric. It relies on KVLs to the extent that we can. And then it easily handles voltage sources, right? We have voltage sources everywhere, and that's not a problem. So handles voltage sources easily. Okay? So now what we might guess is that mesh analysis will have difficulty with current sources, just the way node analysis had difficulty with voltage sources. So here we can handle current sources easily, here we can handle voltage sources easily, and the other way around is a problem for either of them. So that's something we have to think about. We have seen resistors in many of our circuits. So we talked about the flex sensor before as a resistor whose value changes with the amount of flexion or bending that we apply to that strip. But there are other sensors that also have resistance as a characteristic and whose resistance changes with something else in the environment. And those resistors are used in many different places. So in this paper here, they try to conceive a skin for robots. And by that we mean if we have a robot, we want to have some sort of covering for the robot so that the robot can actually feel, for example, pressure from different places. And it's an interesting idea. So here we have a robot. Here's the arm of the robot, the hand of the robot, so to speak. And the hand is covered with what they call sensing skin. The sensing skin contains many sensors, and these sensors are sensitive to pressure. So if this robot arm is placed against something and pressed against something, the sensors can measure that pressure and tell the robot whether the pressure is too much or too little, etc. So you can see that it's actually very useful to be able to do something like this. Now, the sensors in here are actually resistors. And the value of those resistors changes with the pressure. So here they talk about the applications of having a skin for robots. They say we can improve robots' ability to reach locations in clutter, or robots can provide better assistance with some other systems and so on. And the resistors that change value with the pressure are like this. So we have a resistor here inside this sensor, and the value changes depending on the pressure that the sensor senses. And now, just like before, we form a voltage divider using that resistor and a constant resistor. And this is connected to a battery voltage. So as the robot presses against something and the value of the resistance changes, so does this voltage. This voltage changes, we can measure it by some electronics, and then we can tell how much pressure the robot is experiencing. So that's another interesting application where just simple resistors can do a great deal. Isn't that beautiful? Okay, all right, so that was one little example. Let's go and look at another example and see how we're going to handle that. Let's see here. I think I can try to squeeze that example here. Okay, so let's see. We have a circuit like this. We have a voltage source. We call it Vx. Then we have a resistor R1. We have a resistor R2. We have a resistor R3. We have a current source Ix. Then we have another resistor R4, and then we have another resistor R5. And these are all connected like so. Okay. All right, so we have all of these devices connected in this form, and we would like to perform mesh analysis. Again, we can do node analysis, that's fine too, or we can use mesh analysis. All right, so we have 3 steps. Step number 1, identify all of the meshes. How many meshes do we have? Well, we have a mesh here, so let's call that I1. We have a mesh here, let's call that I2. And we have a mesh here, let's call that I3. All right, these are the only meshes that we have. Okay, so we're going to go ahead and in the second step of analysis, write the voltage drops across all of the devices that we can find. So for these resistors, we should be able to write their voltage drops, right? Okay, so change the color again so that the voltage drops stand out. And we have across R1, I1 is going from left to right. So just like what we had here, we have a plus minus, and that's I1 R1. It's a little messy. You just have to draw the circuit really big so that this all can fit in there. Okay, how about R3? I2 is flowing this way, so that gives me a voltage drop like so. And that would be I2 times R3. R3. So this voltage is the voltage drop from here to here. High potential, low potential. The current is going from high potential to low potential. All right, how about R4? I3 is going through R4, so again we have positive, negative here, and that voltage drop is I3 R4. Okay, and finally I have I3 times R5, so that would be like so. The current is going from top to bottom. So it generates a voltage that's high here, low here, and that voltage is given by I3 times R5. Okay, there's only one component that needs special attention, and that's this one, R2. So R2 has a current going down equal to I1, has a current going up equal to I2. That's reminiscent of what we had here, right? Same situation. So the voltage drop across R2 is I1 minus I2 times R2. So this voltage drop is given by I1 minus I2 times R2. So good? Okay, all right. So we have completed the second step of analysis. Now we go to the third step. The third step says write a KVL around every mesh. All right, so we start from here. This mesh is actually very similar to this mesh, right? V1, Vx, R1, R2. So we had this equation for it anyway, so let's write that out. Plus Vx minus I1, R1, then plus this one, which is minus this voltage drop, brings us back to the same point. So our KVLs will be as follows. So KVLs. So I have I1, I have plus Vx, going up to potential, going down to potential here, minus I1 R1, then going down to potential here. So whatever voltage I have here, I have to multiply by minus 1. So minus I1 minus I2 times R2. Coming back to the same point, so that's 0. Okay, that's one KVL. All right. Okay, that's great. Now, let's go to the next mesh and write our KVL. This mesh says, starting, for example, from here, going up to potential. So whatever voltage I have here appears with a positive sign. So plus, the voltage we found was I1 minus I2 times R2, and I'm going up to potential. So that's I1 minus I2 times R2. And then I arrive here, I'm going down the potential, that's I2 R3 with a negative sign. So minus I2 R3. So far so good. Okay, so we went up here, we went down here. Now I'm going to go write the voltage here. Do we have a problem? Yes, we do. How much is the voltage from here to here? I don't know. Because a current source does not satisfy Ohm's law. So I do not know that voltage. Should I call it something? Call it V5? Yes, but then if you call it V5, we introduce a new unknown and we write a new equation. So that doesn't help us, right? This is very similar to the situation of a voltage source in node analysis. For a voltage source, we decided not to assign a current to it, not to call that an unknown. So here we have the same problem with the current source as far as mesh analysis is concerned. We have right here, but now we're stuck, right? We can't say anything about this. We don't know how much this voltage is, and we don't want to call it something because then the number of equations will not be equal to the number of unknowns. And similarly for this one, right? For this one, I have voltage drop for this, another one for this, that's great. But this doesn't have voltage drop on it. We don't know what the voltage drop is, so we have a problem. Okay, so we have an issue here, and this is reminiscent of a voltage source in node analysis, right? Here we have a current source in mesh analysis. So what's the procedure? Well, remember, in node analysis we said that we merge the two nodes that are attached to the voltage source to create a supernode. Here, by duality, we merge the two meshes that share the current source into a super mesh. I repeat, we merge the two meshes, this mesh and this mesh, that share the current source into one super mesh. So super mesh would be this mesh here. All right? Okay, there are at most two meshes sharing a current source, right? There cannot be more. Why? Because mesh is defined as the smallest loop we have. So there can be only two loops that share one current source. You can't possibly have another loop sharing this current source because that loop would include one of these loops. So we can have only two meshes at most sharing one current source. And once that happens, we're going to call these two one giant mesh. We call it a super mesh. So let's write the KVL around the super mesh only. Okay, so we don't write a KVL around these little meshes here because that's not useful. We start from here. We say, okay, here's a mesh. Here's our super mesh. Let's write a KVL around this mesh. We can do that, right? Because it doesn't have a current source anymore. Okay, so we start from here. We're going up the potential. So we got this. So we have I1 minus I2. I1 minus I2 here. Times R2 gives me the voltage. And because I'm going up the potential, this takes a positive sign. And then I'm going down the potential here. That's I2 R3 with a negative sign. So minus I2 R3. So I'm not going down here. I'm continuing within my super mesh. So I get here and I have going down the potential of R4. So that's minus I3 R4. And finally I go down through R5. So that's minus I3 R5 minus I3 R5. And this has to be equal to 0 because I'm coming back to where I started. Right? So that's a legitimate KVL that we have written. Okay, so we have three meshes, but we ended up with two KVLs. Why? Because we have a current source. The current source makes us lose one KVL because we ended up merging two meshes into one super mesh. All right? So you can see the similarity between what we did with supernode, right? Supernode merged two nodes. Here super mesh merges two meshes. Okay, so if I have lost one KVL, what should I do? I should be looking for a KCL. A KCL now should relate the troublesome current source, this current source, and the currents of the two meshes that share this current source. This mesh has a current of I2. This mesh has a current of I3. These two currents and this current source should be related by a KCL. How can they be related? Oh, it's pretty easy. You sit here and look, right? So let's write the KCL. I'll try to squeeze that in here with a different color. Let's see. Okay, so I'm going to write a KCL involving the current source that's giving us trouble and the two meshes that share that current source. So we have Ix flowing out of this node. We have a current flowing into this node. How much is that? That's I2. We have flowing out of this node also this current, I3. So I2 coming in, Ix going out, I3 going out, have to satisfy KCL here. So we're going to write I2, which is coming in, I2 is coming in, and then Ix going out, and then this current, which we call I3, is also going out, plus I3. So now we have one KCL, two legitimate KVLs, and three unknowns, I1, I2, and I3. We can find everything that we need. All right? So if you remember the duality between node analysis and mesh analysis, these things become relatively easy to remember. So what we see is that in the case of mesh analysis, if we have a current source, the current source gives us trouble. And what we do is we merge the two meshes that share that current source into one mesh. So we can write our KVL around that mesh. We lose one KVL. And because we lose one KVL, we look for a KCL involving the current source and the currents of the two meshes that share that current source. So it would be this current, and this current, all at this node. All right, so that's the procedure. So that's the only issue we have to worry about when we are performing mesh analysis, but otherwise the steps are pretty straightforward. Okay, let's see here if I have another point to mention. Okay, so I think that's good. We will move forward to excitation and response, what we mean by these things, and then go to linearity and superposition. So let's go to the next page here. Okay, so we're going to talk about excitation and response. All right, so if we have a circuit, it has a bunch of independent sources, voltage sources and current sources. So we have independent sources. And we can consider these independent sources as excitation. They're exciting the circuit with whatever they're applying. They're applying a current, a voltage. They could be constant, they could be variable in the time domain, whatever they are. They're exciting the circuit. So we call these excitations. Or you can call them inputs, right? So you can also call them also known as inputs. Okay, so if I have a circuit like this, a bunch of devices all connected and so on, and then I have an independent voltage source here, an independent current source here. I can say this is one excitation or input, this is another excitation or input, right? Okay, and then, but remember that only for independent sources. For dependent sources, we cannot say that. They are part of the circuit. They're not coming from outside the circuit. Okay, and then other quantities, are called the response. Response, or you can call them outputs. Responses, and then you can call them outputs. So for example, I have V1 and I1, and as a result of these excitations, there's a current here, right? Some current, call that I5. This current is a result of these two. So that is called the response of the system, or it's called the output of interest in the system. So from another perspective, excitations are the cause and responses are the effect. So we just have to remember those. A simple terminology that comes in handy as we talk about linearity and superposition. Okay, so let's talk about linearity and see what that means. This is a profound and extremely important concept in engineering, electrical engineering, circuit design, everything, so we didn't need to understand that. All right, suppose I have some sort of system or circuit that receives an input. So we call this input x of t, maybe x1 of t. Okay? So it could be a voltage, it could be current, anything you want, right? And then it generates an output. We call this y1 of t. And this output again can be a voltage somewhere, this voltage here, or this current here, somewhere, right? Anywhere you want. Okay. And then what we observe is this. We apply x1, we get y1. And then we apply x2 of t, and we get y2 of t. Right? These could be completely different signals, right? You apply my voice to this microphone, we get something. We apply some music to this microphone, we get something else. All right? Okay. Now, this system, the system that we have performed these experiments on, is considered linear if the following holds. So linearity requires that this condition hold. If I take any multiple of x1, so call it alpha x1 of t, and any multiple of x2, so plus beta x2 of t, and I give this to the same system, what I should see at the output is the same linear combination of these two. So what I should see at the output is the response to this guy scaled by alpha, the response to this guy scaled by beta, and then added to each other. So here, what I should see is alpha y1 of t plus beta y2 of t. If this condition holds, we call the system linear. All right? So if this microphone is a linear device, it means that when my voice goes through it, it generates something. When music goes through it, it generates something else. Now, if at the same time my voice and the music go through the microphone, the results should be still what I got from my voice and what I got from music. It makes sense, right? So the microphone is a linear device. So it's the same thing. So we should always remember this condition, that if I create a linear combination of these inputs and apply it to the system, the output should be the same linear combination of the corresponding outputs. All right? Okay. So if we have that in a system, and most of our circuits are like that, then we arrive at this principle of superposition. And superposition is described as follows. So superposition. So we say in a linear system, now that we have a definition of linearity, the total response to multiple excitations is equal to the sum of the corresponding responses. Okay, so let's take a moment to digest and see what that means. All right, so what this says is that I have a linear system, and I have multiple excitations coming in at the same time. For example, my voice and music at the same time going through this microphone. All right? Now, because the system is linear, we can say that the output of the system, the output of the microphone, has a total response which is equal to the individual responses to those excitations. So if one excitation is alpha x1 of t, my voice, another excitation is beta x2 of t, music, then the response of the system to the whole thing is equal to the response to my voice, meaning this one, plus the response to the music, this one. All right, that's what it means. So you can see that it's just a natural result of linearity. It's really just a different way of saying linearity for a system, right? All that means is that if I want to find the overall response, what I could do is first I find the response of the system to only this guy, while the other guy is 0. And then I find the response to this guy while the other guy is 0. And then I add up the responses, and that will be the total response that I have. So that's the beauty of superposition. And the utility of this idea becomes handy when we are dealing with a circuit that has multiple inputs. For example, a voltage source, you have a current source here. And it's a relatively complicated process to write the equations while both of these are present. So what we do is we set 1 to 0, right? So I set one excitation to 0, and I find the response, for example, this response, resulting from this excitation, meaning alpha y1 of t from this excitation. Then I set the other input to 0, so I set this one to 0 and I keep this one, and I find the response resulting from this guy. I find this response from this guy. And then I add up the results. That will be total response, for example, for that current flowing through the capacitor. So we'll go through some examples to hammer this in, but that's the basic idea. So anytime you have a circuit with multiple inputs or excitations, you can immediately consider superposition, right? Whether it's faster than our previous types of analyses, node analysis, mesh analysis, etc., maybe not. It just depends on what we're trying to do. But in some cases, superposition is extremely helpful. Okay, let's look at the time. We are reaching the end of our lecture. So next time we'll go over some examples of circuits that have multiple inputs. And instead of just writing node analysis or mesh analysis directly, we'll say, okay, let's kill one input, set it to 0, and find our response resulting from 1. Then we kill the other input. We keep this one alive. We find the response resulting from this. And then we add up those responses, and that will be the total response of the system. I will see you next time.